let me give some examples which can use this formula. So the first one is ft equals cos of t. Then first of all note that first remark is that this integral f u over u du exists as an improper Riemann integral, since if you take t to r for cos u du, then this is nothing but sin u from t to r. So this is sin r minus sin t, and this is bounded above by 2, because each term, the first term is bounded above by 1 and the second term is bounded below by minus 1. So this difference is bounded above by 2, and so this integral exists as an improper Riemann integral. On the other hand, if you try to compute the Laplace transform of t to infinity cos u over u du, then by our formula, I missed 1 over s here, there should be a 1 over s. So one has 1 over s, then the integral from 0 to 1 of the Laplace transform of cos of u, which is nothing but lambda over 1 plus lambda squared d lambda. This is from 0 to s, and this is nothing but 1 over 2s log of 1 plus lambda square from 0 to s, and so you get 1 over 2s log of 1 plus s square, valid for s greater than 0. So we see that for cos of t, we get the Laplace transform of the improper Riemann integral from t to infinity cos of u over u as 1 by 2s ln 1 plus s squared. Now similarly, if we take ft to be sine of t, then again we can show that integral from t to infinity sine u over u du exists, and we also have, so this exists for t greater than 0, and we also have that the Laplace transform of this integral du is given by 1 over s times 0 to s, the Laplace transform of sine function, which is 1 over lambda square plus 1 d lambda, and this is nothing but tan inverse of lambda from 0 to s, and this is 1 over s tan inverse of s. Now we have already seen that the Laplace transform of 0 to t sine u over u du, this is 1 over s tan inverse of 1 over s. So this is also valid for, both of them are valid for s greater than 0. So now if we can add these two, this implies that the Laplace transform of 0 to infinity sine u over u du, this is equal to the sum of these two things. So it's 1 over s tan inverse 1 over s plus tan inverse s for s greater than 0. Now we can use the inverse trigonometric formulas to show that this is nothing but pi by 2, and on the left hand side we have, this is a constant, so the Laplace transform of a constant is that constant over s. This implies that the Laplace transform of this the value of this integral 0 to infinity sine u over u du is nothing but pi by 2, because 1 over s will cancel out on both sides. So you can see that the Laplace transform technique is also useful for evaluating integrals like this, if we can know the Laplace transform for the partial integrals. The third one is ft is exponential of minus t. So this is also for t greater than 0, and also we have this integral from t to r exponential minus u du. This is nothing but exponential minus t minus exponential minus r, and this is bounded above by 1. So this also implies by the Dirichlet test that the integral t to infinity exponential minus u over u du exists, and now we can try to evaluate the Laplace transform of this integral du, and this should be 1 over s 0 to s. Now the Laplace transform of e to the power minus u is just 1 over 1 plus lambda, and you have d lambda. So this is valid for s greater than 0. So we get 1 over s log of 1 plus s greater than 0. So this formula comes in handy when we have these kinds of integrals. Now these integrals have a special name. This is called the exponential integral, and the one before for cos t, this is known as the cosine integral. But the sine integral is not this one, but rather this one. So this one is the sine integral. So we have these various important integrals, and these sometimes come up in the theory of ordinary differential equations, and we have to know the Laplace transform of these functions to solve those equations. Now I'll give a sufficient condition for the formula Laplace transform of t to infinity fu over u du equals 1 over s 0 to s f of lambda d lambda to hold. Now this requires some delicate analysis, and it's not always true that one can interchange the order of integration, but we have the following theorem which gives you a sufficient condition. So suppose that I write gn, so this is for each n greater than or equal to 1, a positive integer. I write gn of v as 1 over v integral 0 to n f of tv exponential minus st dt. Then if there exists a function kv such that the modulus of g and v is less than or equal to kv for every n greater than or equal to 1, every natural number n greater than or equal to 1, and the integral from 1 to infinity of kv dv exists, then we can say that integral 0 to infinity exponential minus st 1 to infinity f of tv over v dv dt is equal to 1 to infinity and then 1 over v then you have an integral 0 to infinity f of tv e to the power minus st dt dv. So this order of integration can be changed supposing that we have this condition. So now suppose I would like to verify this theorem. For verify the theorem, the sufficient condition for the change of integrals for our function f u equals sin u. So let's see whether we have whether the conditions of the theorem are validated. So we have g n v equals 1 over v integral 0 to n now sine of t v exponential minus st dt. Now we can evaluate this integral explicitly. The evaluation gives us the following formula. We have 1 over v, then a factor of 1 over s square plus v square, and then we get v minus v cos of ns plus s, there should be a plus sign here. So one can evaluate it and we get the following formula, 1 over s square plus v squared, and then you get v minus s sine of n times v plus v cos of n times v exponential minus ns. Now the modulus of g and v can be bounded by an integrable function as follows. So you have 1 over v times s square plus v squared, and this term is bounded above by v plus s plus v exponential minus s. So we can have this kind of bound, and now let's see that this bound gives you an integrable function. So this will be our k function, and let's see if 1 to infinity k dv, this is kv, exists. So we can rewrite this as 1 over v times 1 plus exponential minus s by s square plus v square. So here one v factor cancels out, and there is another term 1 over v s by s square plus v square e to the power minus s. So we need to understand whether this is integrable over the interval 1 to infinity. So the first part is 1 plus exponential minus s, 1 plus s square plus v square. Let's see if this is integrable, and this is less, first of all this is a positive function, this is always greater than or equal to 0, and this is bounded above by 1 to infinity, some constant you can take here 2 for example, and this is bounded above by 1 over v squared, and this function is finite. It is an integrable function 1 over v square over the interval 1 to infinity, because this is nothing but 1 over minus 1 over v from 1 to infinity, which is nothing but 1. So this is finite, and the second term is 1 to infinity s e to the power minus s by v times s square plus v square dv. So of course all the s parameter things are constant for this integral, so you can take them out. So you have 1 to infinity dv by v times s square plus v square, and now we can make a change of variables to write this as well, you can evaluate this integral directly, but again we can bound it above by this function 1 over v square, because v is greater than 1. So this is less than or equal to dv over v square, which is again finite. So we see that integral 1 to infinity kv dv exists as an improper Riemann integral, and this shows that we can what the formal computation we did for the Laplace transform of the improper Riemann integral from t to infinity sin u over u du, all the computations make sense and they are justified.